Welcome back to the Art of Climate Modeling. In today's lecture, we'll be turning our attention away from dynamical cores and taking a deeper look at the hardware actually running our models. Most operationally developed global climate models require supercomputers. Since the achievable grid spacing and relative complexity of these models are determined by the amount of computing power at your disposal, it's important to understand the principles governing these systems. The outline of today's discussion is as follows. First, we'll talk about supercomputer architectures and trends in supercomputer design. Second, we'll talk about programming models and how they can improve model throughput. Finally, we'll touch on how trends in supercomputing are playing out when it comes to global climate models. An understanding of supercomputer architecture is important when running climate modeling systems, as, inevitably, it is up to the user to specify how many threads should be employed over how many processors and nodes. These terms may seem somewhat opaque before understanding what exactly they refer to. The von Neumann architecture, as depicted here, represents the basic building block of modern computing systems. The first component is the memory unit, which is a large space for storage of data and programs. The second component is the CPU, or central processing unit, which consists of three subcomponents, including memory registers, an arithmetic logic unit, and a control unit. The memory registers on the CPU provide much less storage than the memory unit, but can be accessed much more quickly because they reside on the CPU itself. Data and programs are brought in from the memory unit through a bus, which carries information between the memory unit and CPU. Within the CPU, the arithmetic logic unit, or ALU, is responsible for actually performing computations with the data stored in the memory registers, including additions, multiplications, and other such operations. And the control unit is responsible for maintaining the system timer and for handling requests to retrieve data from input, output, or the memory unit. Finally, user input is received through input and output peripherals, or through a network interconnect, which is responsible for communicating data from outside of the system. Modern CPUs generally include multiple cores, each capable of doing independent computations. These cores each incorporate independent control units, ALUs, and cache. A master controller is present on the CPU to coordinate execution across cores and to manage access to data off of the processor. Multi-core systems are effective when there are multiple computations to be done in parallel with approximately the same workload. For example, if we can break up the global atmospheric grid into multiple chunks and update each chunk separately, then we can spread out the workload evenly among CPUs. Most supercomputing systems are also multiprocessor systems, meaning that multiple CPUs are mounted within a single node with a shared memory unit. This again enables higher performance when there are multiple parallel tasks to be performed. Cheyenne is an example of such a multi-core, multiprocessor system, with 145,152 processor cores total, distributed among 4,032 compute nodes. Each node is dual socket, meaning there are two processor cores per node. Each processor core is an Intel Xeon processor with 18 cores per CPU. Both CPUs share the 256 gigabytes of memory per node. Here's a picture of what a supercomputer looks like on the inside. Supercomputers generally consist of multiple racks, effectively different drawers in a big dresser. If you pull out one drawer, you'll find a single node of the supercomputing system. Each node basically follows the von Neumann architecture, including CPUs, memory, and input-output connectors. Each CPU then consists of multiple cores, each capable of performing a simultaneous computation. The memory unit on each node is shared, meaning that each of the cores within a node can access the memory unit. Given the growing importance of graphical processing units, or GPUs, for modern computation, it's also important to understand how they're different from CPUs. A GPU is generally complementary to a CPU, which is still responsible for managing input and output from the node. GPUs add another layer of complexity to the mix in order to enhance the performance of parallel codes. GPUs consist of many microprocessors, each containing multiple lightweight cores. Generally, these cores have a smaller instruction set than those available on a CPU. To give an example, the NVIDIA GTX Titan X GPU consists of 28 streaming microprocessors with 128 cores each, yielding 3,584 total cores simply on the GPU. In order to understand how CPUs or GPUs operate, and to contextualize future trends in these supercomputing systems, it's important to first understand the fundamental building block of these systems, namely transistors. Transistors are semiconductor devices used to amplify or switch electronic signals and electrical power. They consist of three connections: the source, the drain, and the gate. When power is supplied to the gate connection, electricity is free to move from the source to the drain. When power is removed, electrons are blocked from moving from the source to the drain. With this basic building block, we can construct logic gates, which are responsible for performing very basic Boolean operations. An AND operation, or OR operation, requires 3 transistors, while NANDs or NORs require 2 transistors. The first transistors from 1947 were around 5 centimeters across. Here we see a shot of the first point contact transistor under examination by its inventors, American physicists John Bardeen and Walter Brattain, while working under William Shockley at Bell Labs. Transistors are fundamental building blocks of all modern electronics and are considered by some to be the greatest invention of the 20th century. In 1959, the metal oxide semiconductor field effect transistor, MOSFET, also known as the MOS transistor, was invented by Muhammad Atallah and Daewon Kang. This paved the way for miniaturization and mass production of transistors for use in modern computing systems. After decades of advances, modern transistors are now only around 200 atoms across, operating at a size where quantum effects such as tunneling can be a problem. The left shot here shows 32 nanometer planar transistors, a standard employed from the late 2000s. The right shows the 22 nanometer tri-gate transistors, which are used in the Intel Haswell processors featured in the Department of Energy Cori supercomputer. The National Center for Atmospheric Research Cheyenne supercomputer uses the Broadwell Intel Xeon cores, which boast an even smaller 14 nanometer manufacturing process. Modern thin field effect transistors have been manufactured at the 7 nanometer and 5 nanometer scale. Modern 3D tri-gate transistors look like the figure here, again as implemented in the Intel Haswell processors. This particular transistor design was introduced with the Intel Ivy Bridge architecture and features conducting channels on 3 sides of a vertical thin structure. These 3D transistors are increasingly employed because they overcome previous size barriers related to the employ of 2D transistors. As noted before, transistors are continuously becoming smaller and smaller. The tri-gate architecture with a 22 nanometer process is roughly a quarter of the width of an influenza virus. Recently, chip designs have been moving towards using Samsung's 8 nanometer process, or TSMC's 7 nanometer process, about 12 times smaller than the influenza virus. Modern NVIDIA graphical processing units, including the Ampere architecture, are also using this finer scale process. The continued march of miniaturization remains impressive as new designs are pushing the boundaries of what was thought to be feasible. New thin field effect transistors are now being reduced to only a few nanometers. Unfortunately, this means that this video will likely be dated by the next time this class rolls around. A consequence of the miniaturization of transistors and innovations in manufacturing process has led to Moore's law holding steady for the past 50 years. Originally formulated by Gordon Moore in 1967, Moore's law states that the number of transistors per silicon chip doubles approximately every 2 years. This is not a physical law, of course, and more of a self-fulfilling prophecy based on an observation and projection of a historical trend. In the early 1970s, chips featured around 2,000 transistors, which increased to around 40,000 in 1980, 500,000 in 1990, 20 million in 2000, 500 million in 2010, and around 10 billion transistors in 2020. Industry has noted that this pace has slowed somewhat since 2010 and is now operating at a doubling in the number of transistors on more of a 2.5-year-long cadence. Note that Moore's law does not say anything about computational performance. This is another so-called law known as House's law, but one that stopped holding true in the 2000s because manufacturers no longer increased clock speed and focused instead on parallel architectures and better performance per watt. Per chip power consumption simply became too high to sustain performance at its previous rate of growth, as there were issues with dissipating heat from those chips. In the early 2000s, acknowledging that heat dissipation, power consumption, and miniaturization would be problematic going forward, investments have been made instead in increasing the number of logical cores per microprocessor. In particular, power density became too high, memory system speed couldn't keep up with processor speed, and less benefit was being realized from adding complexity to the instruction set on a chip. As a consequence, these monolithic single processors were broken up into multiple cores. The number of cores per socket has steadily increased ever since. The shift to chips with multiple cores has allowed for chip makers to keep up with Moore's law and led to dual-core chips, quad-core chips, and other familiar products. Single-threaded performance has only increased at 21% per year, and clock frequency has remained almost steady. However, this shift to parallel architectures has been a game-changer for supercomputing systems. In order for system performance to continue its march forward, there is an increasing push toward GPUs, which have allowed for thousands of processor cores as part of a single unit. Performance improvements for individual processors have translated directly into performance improvements in our supercomputing systems. The website top500.org tracks the top 500 supercomputers in the world at any given time, as well as amalgamating all manner of metadata and statistics on the builds of those systems. The chart on the right here shows the performance of the top supercomputer in the world in orange, the number 500 supercomputer in blue, and the sum of all top 500 systems in green. The y-axis here is in number of floating point operations per second, while the x-axis is in year. Notably, the y-axis here uses a logarithmic scale, and so any straight line on this plot corresponds to exponential growth in processing power. For reference, a single NVIDIA Titan X Pascal GPU appears on this chart at the 10 teraflop per second level, while a GeForce GTX 960M is around 1 teraflop per second. The CPU on my MacBook, an Intel Core i7-4870HQ, appears around 100 gigaflop per second. Namely, back in 2002, this MacBook would have been one of the top 500 supercomputing systems in the world. This chart does emphasize how GPUs are amazing workhorses for performing floating point computations. As noted before, CPU performance per watt has been relatively stagnant over recent years, reflecting how CPU systems are too energy intensive. Compared with CPUs, GPUs offer around a 3 times speed up per watt. Supercomputing agencies from around the world have picked up on this trend, and now 141 of the top supercomputing systems in the world incorporate these NVIDIA GPUs. In the US, the Department of Energy, which maintains the highest-end compute facilities, intends to use GPUs almost exclusively in its most powerful systems, including Perlmutter in 2021 and forthcoming Frontier and Aurora systems. Although improvements in CPU and GPU architecture have enabled more floating point operations per second, memory access times have not kept pace. This has led to a memory access bottleneck that is anticipated to only get worse in the future. Namely, although GPUs and CPUs are becoming quicker at performing computation, the rate at which data can be brought into memory has not seen significant improvement. This suggests a need for the design of supercomputer programs that do more work with fewer memory accesses. Namely, we need to consider future program designs where individual computations are free, but memory accesses are costly. Now that we've discussed hardware architectures and associated trends, let's turn our attention to the software systems that run on these platforms and how they take advantage of the parallelism of the hardware. Flynn's taxonomy provides a scheme for classifying computer architectures based on how instructions and data interoperate. Along the vertical axis, we have the number of instruction sets that are handled by the software system, referring to either a single instruction set or multiple instruction sets. Multiple instructions can refer to either multiple programs run simultaneously, or the same program being run by multiple processors, each being at potentially different points in the program. Along the horizontal axis, we have the number of data elements, either single data per operation or multiple data per operation. In general, MISD is an uncommon and not particularly useful architecture, so we'll neglect it from this classification. The simplest model in Flynn's taxonomy is the single instruction, single data paradigm. This type of architecture can operate on a single data stream at a time and perform instructions from a single computer program. This type of architecture is associated with a single core, single processor computer system. In the example here, our program loads two data elements from memory, performs an operation on them, then writes data back to memory. Parallelization refers to the employ of multiple processors, each performing computations in parallel. One such example of a parallel architecture is the MIMD, or Multiple Instruction Multiple Data Architecture. In this case, each processor is running a different instruction set on different data streams. This is the most general form of parallel computer and typical of modern CPUs. However, GPUs follow a different architectural structure that is close to the SIMD, or Single Instruction Multiple Data model. By running the same instruction set over multiple components of the same data vector, the GPU cores can be simplified and produce better parallel performance. The control systems thus can be pulled out of each core and placed within the microprocessors that control the whole set of cores. Computations performed in this manner are referred to as vectorized computations, since operations are performed on vectors of data rather than single data elements. As we discussed earlier, supercomputing systems are comprised of multiple nodes, each consisting of one or more CPUs and an associated memory unit. This particular model is referred to as a distributed memory system, since there is a distinction between data that is local and data that is not. Local data is more easily accessed by a local CPU, while accessing data on another node requires communication over the network that can greatly slow down the computation. Hybrid distributed shared memory systems refer to multiprocessor or multi-core systems within each node. In this case, multiple computations are performed locally, while data exchanges may be going on globally. Care must be taken when performing local computations to avoid collisions between the operations from multiple processors. Namely, if one processor is trying to read a particular data element while another processor is trying to write it, the result is generally unclear. Most modern parallel codes use a combination of the message passing model and the threads model. One such implementation of the message passing model is the message passing interface, or MPI. MPI is a standard most commonly used for distributed memory systems that allows messages to be exchanged between nodes, although it can also be used in a shared memory environment. MPI enables programs to assemble messages containing data that can then be sent between simultaneously running programs. One such implementation of the threading model is OpenMP, which is used for managing computations on shared memory systems. In particular, OpenMP enables work being performed in a shared memory space to be distributed evenly among processors. Of course, in the case of multiple cores on a single node, programs may need to support both MPI and OpenMP. While OpenMP can be used within each node, MPI is needed for communicating information between nodes. Other programming models are now available that expose parallelism in new ways. For example, there are high-level libraries such as Legion, HPX, or Parsec, which allow developers to find new sources of parallelism in their codes. There are other threading libraries such as pthreads or PPL, which operate analogous to OpenMP. There are libraries that allow codes to view distributed memory as a single global address space, such as GasNet or UPC++. Finally, there are data models that allow for code portability between architectures, such as COCOS and OCR. All of these programming models are now rising to prominence because of the pressing need to write codes that work on a variety of supercomputing architectures. So what does this all mean when it comes to the implementation of global climate modeling systems? What do we have to keep in mind? Well, there are a few things to think about when trying to maximize performance of parallel applications. First off, we need to ensure that work is equally partitioned among processors, and no processors are left waiting on others. While this is essential to ensuring programs work well on large numbers of processors, this is also easier said than done. Second, we need to ensure that patches of data assigned to a single processor are compact so as to minimize the amount of data that needs to be exchanged. Further, we need to avoid global solvers or implicit methods, which require messages to be sent from essentially every processor to every other processor. Third, we need flexible expressions of parallelism that enable model codes to work regardless of the underlying programming model. We want codes that work well with messages, threads, or under SIMD architectures such as we'd find on a GPU. Finally, we want a small memory footprint per thread, meaning that we need to choose numerical methods that require more computation for each memory access. This immediately points to high-order but compact numerical schemes such as finite element methods. On the topic of equal partitioning of work, there is simply more to it than distributing an equal number of grid points to each processor. Not every grid point requires the same computational load, and that imbalance can easily result in some processors waiting on others. Consider that at any given time, only half the planet is exposed to sunlight. When the sun is present, there is far more to compute. We need to model the impact of short wavelength radiation on the thermodynamics and chemistry of the environment. Thus, distributing equal patches of data to each processor can still produce unequal work. One common solution to this problem is to assign to a single processor 2 grid patches on opposite sides of the planet from one another. Then each processor will be managing an equal number of day and night points, and so will have more even distribution of work. With that said, this philosophy only really works for uniform grids. Variable resolution or regionally refined grids add another layer of complexity to this problem. On the topic of maximizing locality, we know that not all numerical methods are created equal. As discussed previously, both the CAM-FV dynamical core and the CAM-Eulerian dynamical core include calculations that require exchange of information across a large number of processors. The highly local spectral element dynamical core, on the other hand, requires minimal exchange with neighboring processors and boasts a large number of calculations for each memory read. As a consequence, the spectral element dicore achieves near perfect scalability as the number of processors is increased. In fact, because of investments made in the software engineering of these models, it's not uncommon nowadays for atmospheric modeling systems to boast similar scalability. Here we see results from the global 13-kilometer high-WIP benchmark, which was used to select the model for the newest version of NOAA's global forecasting system. In general, all the models show excellent parallel scalability, even at large core counts. While near-perfect atmospheric model scalability can be achieved with the right choice of numerical methods, the equation sets governing ocean and ice models make it more difficult to develop highly scalable numerical methods. Enforcement of the incompressibility condition for water and ice leads to a global exchange of information at each time step, which can make it more difficult to achieve parallel scalability. Nonetheless, work continues on the development of new numerical methods for all components of the Earth system. Let's discuss briefly how computational power relates to permitted atmospheric model resolution. Following up on recent trends in supercomputer performance, we find that computational power roughly doubles every 1.2 years. Consider now that to obtain a factor of 2 in horizontal refinement, that is, a halving of delta x, we require 8 times the computing power. The 8 times in this case comes from a doubling in the number of elements in each horizontal coordinate direction, along with a halving of the time step size imposed by the CFL condition. This suggests that we should observe a doubling of horizontal model resolution approximately every 3.6 years. Obviously, this is a bit of an idealization, as model complexity is advancing simultaneously and vertical resolution is also being added. But one would think that it's not a bad estimate of reality. Global Modeling Center's contributions to the Ipcc assessment reports provide us with a means to understand the typical resolutions of global modeling systems. The first assessment report in 1990 used simulations for models at approximately 500-kilometer global resolution. 5 years later, for the second assessment report, average model grid spacing was halved to 250 kilometers. The third assessment report in 2001 provided only a slight increase in model resolution, with average model resolution being around 180 kilometers. Then, for the fourth assessment report in 2007, resolution was dropped to about 110 kilometers, or 1 degree globally. Since then, the average CMIP class model has remained stubbornly stuck at approximately 1 degree global resolution. While some intercomparison efforts, such as HiResMIP and Diamond, have permitted model simulations at higher resolutions, these are not generally employed for understanding climate change. Unfortunately, This suggests that model resolution is not at all keeping pace with supercomputer performance. Here we see a more detailed plot from Schneider et al. 2017 of how model horizontal resolution has been advancing. Each filled circle represents an atmospheric general circulation model, each open circle a coupled atmosphere-ocean general circulation model, and each open diamond a full Earth system model. The blue line represents the advancing supercomputer performance of these supercomputer systems. This further emphasizes how our climate models are advancing relatively slowly versus available computing power. With that said, some big strides are being made in building the next generation of global climate modeling systems. One recent effort is the DIAMOND Initiative, short for Dynamics of the Atmospheric General Circulation Modeled on Non-Hydrostatic Domains. Within the project, modelers from around the globe were invited to contribute 40-day simulations at resolutions of 5 km and finer. The resulting simulations led to plots that were hard to distinguish from satellite photography. With that said, substantial work remains before these simulations are scientifically vetted and can be used for climate change understanding. In summary, advances in hardware models are forcing us to rethink our software systems. Model codes now need to be designed to be robust across different hardware designs and across multiple levels. New supercomputer designs, including graphical processing units, are adding a new level to the hierarchy in order to improve throughput for certain kinds of calculations. Further, while past advances in model resolution have been slow, improvements in supercomputer performance are enabling deeper exploration of Earth system science through large ensembles and shorter, extremely high-resolution simulations. Okay, that wraps up our discussion on supercomputing and its applications to global climate modeling. Next time, we'll be talking about how we can use variable resolution modeling systems to improve local resolution and overcome some of the bottlenecks with model performance at scale.